Good morning, students. Before starting the problems related with the compressor, we have to see the just brief review. First, we are going to see the methods of improving the isothermal efficiency. Now, the methods which we are going to be used for increasing or improving the isothermal efficiency, we have discussed previously. So just first we are going to provide the external fins, so the cooling effect will be increased. Then spraying injection we are providing the perfect intercooling. Then water jacketings we are providing, intercooling we are going to provide, and by suitable choice of the cylinder. So here we are finding that the H is equal to W dash upon W. We are finding that W dash is equal to P1 V1 ln of P2 upon P1 upon N minus 1 P1 V1 P2 upon P1 raised to N minus 1 upon N minus of 1. So this is the improvement factor you got by applying the some above said methods. Now the volumetric efficiency we have discussed that the ratio of free air delivery to the displacement of the compressor. So the volumetric efficiency is equal to effective stroke volume upon the stroke volume. So we have find that volumetric efficiency, effective stroke volume is V1 minus V4, and the stroke volume is the V1 minus V3. So volumetric efficiency we got from this formula. Next, clearance ratio. We are indicating C means clearance ratio. We have seen this C in the minimum work done derivation. So that C, that is the clearance volume, we have find that C is equal to clearance volume upon the stroke volume we have derived there. So the C is equal to V3 upon V1 minus V3. So we are saying C is equal to clearance volume upon the stroke volume, so Vc upon Vs. So we got the volumetric efficiency is equal to 1 minus C into bracket P2 upon P1 raised to 1 upon N minus of 1. Now we are going to discuss the power formulas. Power of a single stage compressor. So we know that P is equal to W upon NW upon 60. So NW is number of working stroke, and NW for N is equal to N of the speed of the compressor. When it is double acting, N is equal to twice N. So isothermal power we got P is equal to W into N W upon 60 watts. So from this formula we got the isothermal power. Indicated power we got P is equal to W into N W upon 60. This is also in watt, so this is the indicated power, and isentropic power P is equal to W double dash NW upon 60 watt. So here W dash it is the isentropic work we have finding, that is the we are saying adiabatic work, also reversible adiabatic work. So by using that reversible adiabatic work we are finding the power. So when the process is isothermal, we are using the isothermal power. When there is a polytropic process, we are using the polytropic process power, whatever we are using, that is the indicated power we are saying it as a. And when we are using the isentropic process there, then we are finding the isentropic power. So in this way we can calculate the power of a single stage compressor. So next, as we have discussed, mechanical efficiency for the engine is BP upon IP, but for compressor it is the IP upon BP. So we are finding the ratio of the IP to BP is called as the mechanical efficiency of the compressor. So we are writing mathematical form, mechanical efficiency is equal to IP upon BP. Now mean effective pressure is equal to W upon Vs. W is the work which we are going to be found, and Vs is the swept volume. So we got here W is equal to Pm into Vs. So Pm into Vs means the work done. So as per the process, N upon N minus 1 PA into VA, whatever the actual volume sucked inside the compressor, we are indicating it with VA, P2 upon P1 raised to N minus 1 upon N minus of 1. So this is work done we have find, and so PM mean effective pressure, we are finding that N upon N minus 1 PA P1 into VA upon Vs. So the VA upon Vs is the, we know that the volumetric efficiency. So into bracket P2 upon P1 raised to N minus 1 upon N minus of 1. So we got mean effective pressure is equal to N upon N minus 1 P1 into volumetric efficiency into bracket P2 upon P1 raised to N minus 1 upon N minus of 1. So this is the mean. In this way we can calculate the mean effective pressure. So we required that polytropic index must be mentioned over there. Then we know that the P1 value, that is the atmospheric pressure we are taking, volumetric efficiency must be mentioned over there. If it is not mentioned, then there must be actual volume inhaled and the stroke volume must be mentioned over there. And pressure, discharge pressure definitely we knows, and inlet pressure we knows over there. So just if these values are given in the problem, we can easily calculate the mean effective pressure. We have also seen the free air delivery. So isolate compressor and receiver, and close receiver outlet, and empty the receiver and the pipeline from the water. Start the compressor and activate the stopwatch. Note time to attain the normal operational pressure, that P2 is reached from initial pressure P1, and calculate the capacity of the free air delivery. Now here you can considering P2 is the final pressure after filling, it is in kg per centimeter square. P1 is the initial pressure, it is again in kg per centimeter square. Now PO is the atmospheric pressure we are finding. V is the storage volume in meter cube, which includes receiver after cooler and delivering piping, and T is the time taken to build up the pressure P2 in minutes. So in this way we can calculate Q. Q is the capacity, or we are saying it as a free air delivery, that is P2 minus P1 upon PO into V upon T in Newton per meter cube per minute. So in this way we can calculate the capacity of the compressor, or we are saying it as the free air delivery. So this is the experimental procedure to calculate free air delivery or capacity of the compressor. Now just one more point remaining, that is advantages and disadvantages of the multi-staging of the compressor. Just before that we are going to discuss once again that two-stage reciprocating air compressor. Now you can find in this figure, that is stage 1, stage 2, stage 3, and between these we are providing the intercooling, and at stage 1 the air will be sucked from the atmosphere. So that's why we are showing it as a in, and after stage 3 we are saying it as a out. So between these we have provided stage 2 and the 2 intercoolers over there, and one prime more we have shown over in this diagram. Now when it is required to deliver the gases at or air at a high pressure, it is advantageous to compress the air or gas more than one cylinder with intercooling between the stages, and this method of the compression is known as the multi-staging of the compressor. Now, advantages of multi-staging of the compressor, we are finding that there is a saving in a work input due to intercooling, high volumetric efficiency can be achieved, smaller flywheel needed, exhaust temperature of air after multi-stage is low compared to single stage, so this reduces the lubrication problem, less leakages problem are faced due to reduced pressure difference for each stage, better mechanical balance we got over here, and disadvantage is more expensive initial cost is required in single stage compressor for the same capacity. So this is one only disadvantage is the we require the more expense for the initial level, but after that so many advantages in the multi-staging of the compressor. Now we have derived work done formula for with perfect intercooling. Now with intercooling for low pressure cylinder we have shown the area 8 to 1, 1 to 4, 4 to 7, 7 to 8, and for high pressure we are getting the area 7 to 2, 2 to 3, 3 to 6, 6 to 7. So we know that T2 is equal to T1 and P2 V2 is equal to P1 V1. So also we know that P4 is equal to P2. So from this we got the work done, that is n upon n minus 1 P1 V1 into bracket 2 minus P2 upon P1 raised to n minus 1 upon n minus of P3 upon P2 raised to n minus 1 upon n. So now this work done, so when there is a perfect intercooling between the stages, we have saved some amount of the work. So shaded portion in this figure on the PV plotting you are finding 2 to 4, 4 to 5, 5 to 3, 3 to 1. This is the saving of the work due to the intercooling. So we have find the work done for the perfect intercooling, and we have saved the work as shown in the shaded portion in the PV diagram. Now two-stage compressor. Now we have seen the different processes, that is polytropic process, isothermal process, and whenever we plot these processes on the PV and TS plotting, you find that various regions we got, and we got the three pressure, that is P1, P2 and P3. So how we are showing it PV and TS plotting, this is shown over here. Now here you are finding that intercooling, during this intercooling we are finding that we are keeping the pressure line, it lies on the pressure line, so it is the constant over there, and the colored area on the PV diagram, this represents the work saved as a result of the two-stage compressor with the intercooling. So this is the main advantages, or this is the area we have finding for the saving the work for the different processes. Now we are going to discuss minimum work required for two-stage compressor. Now minimum work we have derived the formula, that is twice n upon n minus 1 P1 V1 into bracket P3 upon P1 raised to n minus 1 upon twice n minus of 1. Now if n is the number of stages, then the condition minimum work required, we are saying it as a P2 upon P1 is equal to P3 upon P2 is equal to P4 upon P3 up to so on. So here P n plus 1 upon Pn, we are saying it as a constant ratio, and we are finding, so from this we can say that as a Z we are going to be introduced, so Z is equal to P2 upon P1 which is equal to Pn plus 1 upon P1 raised to 1 upon n, or we are saying it as a pressure ratio through the compressor raised to 1 upon n. So we got W minimum, that is work minimum required, is n, capital N into small n upon n minus 1 p1 v1 into bracket pn plus 1 upon p1 raised to n minus 1 upon n capital N into small n minus of 1. So this is the minimum work we are finding for the, suppose there are n number of stages we are using. Now pressure ratio for number of stages, that is we are saying it as a x stages, we do the know that the minimum work we have just derived. So in this formula the pressure ratio of each stage is the same. So we can write P2 upon P1 is equal to P3 upon P2 is equal to P4 upon P3. So which is equal to P of x plus 1 upon P1. We are saying it as a y. So therefore P2 upon Yp1 P3 is equal to y square into P1. So P4 is equal to y3 into P1. So y is equal to x into square root of P into brackets x plus 1 upon P1 into pressure ratio through the compressor. So this is the pressure ratio we are getting over here for multi-stage. Now we are going to discuss one more point, capacity control of the compressor. So in practice the compressor are not running continuously all the time at their maximum rated capacity. So therefore it is essential that some means are provided to control the amount of air supplied by it in order to meet the required demand. So the method of controlling air delivered are throttle control, clearance control or blow off control. So just we are going to brief review that comparison between the reciprocating compressor and the rotary compressor. Here you can find in reciprocating compressor delivery pressure is up to the 1000 bar, but in rotary compressor the maximum delivery pressure is up to the 40 bar. Now these reciprocating compressor are suitable for low discharge and the high pressure, and the rotary compressor are suitable for high discharge and the low pressure. Air discharge is not continuous, so the receiver is needed in the reciprocating compressor, but in case of the rotary compressor air discharge is the continuous. This is main advantages of the rotary compressor, so receiver is not needed in case of the rotary compressor. And it is required to complicated lubrication required in case of reciprocating compressor, but in case of the rotary compressor simple lubrication system is required. In case of reciprocating compressor size of the compressor is large than the rotary compressor, but in case of the rotary compressor size of compressor is smaller, and due to reciprocating parts balancing is required, and it is the major problem in the reciprocating compressor. No reciprocating parts, so balancing is not a big issue. So this is advantageous in case of the rotary compressor. Maintenance cost is more in reciprocating compressor, and in rotary compressor it is less. So due to clearance volume efficiency is less than 100% here in case of the reciprocating compressor, and in rotary compressor as we are not providing any kind of the clearance volume, so the efficiency is the high 100%, and the running cost is more in case of the reciprocating compressor, and in case of rotary compressor running cost is the less. So these are the comparative points in the reciprocating compressor and the rotary compressor. So In this slide we can see that the single stage compressor without clearance, we have drawn the PV plotting and some of the important formulas such as the indicated power is IP is equal to W into N upon 60,000, where small n is equal to capital N for single acting compressor and n is equal to twice N for double acting compressor. We have shown isothermal efficiency, we can calculate P1 V1 ln of V1 upon V2 and P1 V1 ln of P2 upon P1 also we in pressure ratio we can say, and also we are saying that MRT1 ln of P2 upon P1 because PV is equal to MRT. W actually that is W polytropic if we are considering n upon n minus 1 P1 V1 P2 upon P1 raised to n minus 1 upon n minus of 1, or we are saying it as a gamma upon gamma minus 1 P1 V1 P2 upon P1 raised to gamma minus 1 upon gamma minus of 1. So just we are substituting the PV equal to MRT value. So we got n upon n minus 1 MRT1 P2 upon P1 raised to n minus 1 upon n minus of 1. So this is the actual work we are finding. Then isothermal efficiency is equal to isothermal work upon the actual work, and the mechanical efficiency we are finding the indicated power upon brake power, or we are saying brake power as a shaft power in case of the compressor. So V1 is equal to Vs, we are finding pi by 4 d square into ln, where we are finding n is the stroke of the cylinder, d is the diameter of the bore, and n is equal to whenever we are going to substitute the n, n is equal to for single acting compressor and double acting compressor, just we have discussed previously, n is equal to capital N for single acting, n is equal to twice n for double acting, and Vs is the stroke of the cylinder we are finding. And just one relation between the temperature and the pressure for the polytropic process and the adiabatic process, that is the T2 upon T1 is equal to P2 upon P1 raised to n minus 1 upon n, P2 upon P1 raised to gamma minus 1 upon gamma. So free air delivery FAD at NTP is not given, so P1 V1 is equal to MRT1. So V1 if we are going to be find over here. So these are the formulas related with the single stage compressor without clearance volume. Now in next slide you can see here single stage compressor with clearance we have plotted on the PV diagram. And in PV diagram we are getting, after PV diagram we are giving some formulas, that is the volumetric efficiency is equal to free air delivery upon the piston displacement. So we got free air delivery V1 minus V4 upon the Vs. So that is the piston displacement we got, or we are saying it in short formula 1 minus Rp raised to 1 upon n minus of 1 into C, where you can see the clearance volume, that is the Vc, and Rp is the pressure ratio P2 upon P1, C is the clearance ratio, that is Vc upon Vs, and we have the relation P into bracket V1 minus V4 which is equal to MRT1. So this is the volumetric efficiency and these formulas, and work when polytropic process is there, n upon n minus 1 P1 into bracket V1 minus V4, just we have discussed we have calculated previously, P2 upon P1 raised to n minus 1 upon n minus of 1. When we are considering adiabatic process, gamma upon gamma minus 1 P1 V minus V4 P2 upon P1 raised to gamma minus 1 upon gamma minus of 1. So for P1 V1 minus V4 we are substituting the MRT1 also. So the formula becomes n upon n minus 1 MRT1 P1 P2 upon P1 raised to n minus 1 upon n minus of 1. So free air delivery here we got P1 into bracket V1 minus V4, which is equal to mRT1. So we are saying V1 minus V4 is the free air delivery. Now in last, that is the multi-stage of compressor, we have plotted the PV diagram, and for this we got the minimum work condition, that is P2 is equal to P1 under root of the P1 into P3. So this is the minimum during the minimum work condition, the relation between the pressures we have finding, and the that is pressure ratio, that is the P2 upon P1 is equal to P3 upon P2 and P4 upon P3. So this is the compression ratios we are finding in case of the multi-staging of the compressor. And we got the work number of stages n upon n minus 1 mRT1, P2 upon P1 raised to n minus 1 upon n minus of 1. So this is the work output we got for each stages. And isothermal work done, that is the mRT1, maximum pressure upon the minimum pressure, where in the compressor if perfect intercooling is the perfect, that is T1 is equal to T2 dash, which is equal to T3 dash, which is equal to T4 dash. And the heat rejected in the intercooler, we have the formula, general formula we have discussed, that is Q is equal to mCp delta T. So in this, for here we are going to substitute the values. Q is equal to mCp into T2 minus T2 dash. So today we have discussed the various formulas related with this unit. We have discussed the various comparisons. This is related with the today's lecture. From tomorrow onwards we are going to start the problem related with the compressor. Thank you.